we'll look at a fairly simple composite shape to start off applying the tabular method for finding the area and the centroid of our shapes. So if we look at the shape that's given to us, we are not told its functional relationship. We don't know the x and y function that defines our shape. However, looking at it, it appears that we can break it down into smaller shapes whose centroids, whose areas we can calculate pretty easily. So looking at here, we can break it down into there's something that looks like a triangle, there's rectangular pieces here, so we can partition this shape into subshapes. As a rule of thumb, when we are using the tabular method, we want to first, if we can, minimize the total number of shapes that we're using. That way there's just fewer rows to fill out in the table, there's fewer calculations that we need to do. So first priority, what's the fewest number of shapes that we can partition this into? Then, for any number of partition shapes we can make, we would rather use positive shapes than negative shapes. And this is just because it's easier to make a sign error or forget to put a negative area in if we are cutting out a shape than when we are usually using positive shapes. These are just rules of thumb. We are not obligated to minimize the number of shapes or only use positive shapes, but it's just a good habit for avoiding making mistakes or making it an overly complicated problem. So looking at this, the one way that we could partition this shape is we have this triangle, and then I'm going to say I have one positive rectangle and then a third positive rectangle. Actually, it's going to turn out to be a square. So there's not a unique way to partition this, but this is probably going to be the most efficient way, is this right triangle, this 2x3 rectangle, and this 1x1 square. Now alternatively, I could have had this 3x3 rectangle as a shape, and then I could have cut out this shape, this 2x1 rectangle from it. That would have also been 3 total shapes, but it would have been 2 positive and a negative shape. So nothing wrong with that, but this using 3 positive shapes is less likely to result in a calculation error. So now that we've partitioned our shape, what we want to do is fill out our table that's going to give us all the information we need to find the area of this shape and where its centroid is located. So if we look at the first row, this is for subshape 1, that right triangle. So I need to fill in what its area is. Everything here is, all dimensions are in feet, so the area will be in square feet. This right triangle has a base of 3 feet and a height of 3 feet. So its area, 1/2 base times height, 4.5 square feet. I like to usually fill out all the areas first, then the centroidal locations, and then do the rest from there. So shape number 2, this rectangle is 2 feet by 3 feet, so an area of 2 times 3 is 6. And shape number 3, 1 foot by 1 foot, is a square area of 1 square foot. Now we can move on to the centroidal locations. So for shape number 1, we have this right triangle. The centroid of a right triangle is located 1/3 of its base and 1/3 of its height from the right angle. Now here we want to pay particular attention to where the origin of our system is. So we were just given this shape and we were given a coordinate system, so I'm just going to stick with the one that we were given. If we're not given a coordinate system, we can establish our own, but we're always going to measure everything from that common origin, from that common coordinate system. So for our coordinate system, this shape 1 has the origin as its bottom left corner. The centroid, let's go with the x direction first. For shape number 1, 1/3 of its base, that's going to be 1 foot away from that right angle. So that takes us 1 foot to the right of the origin, so that's +1 in the x direction. However, if we go to shape number 2, I'll just do x directions for now. It's a rectangle, so its centroid is located at half of its width and half of its height. I'll just look at width for now. So that means 1 foot from the right side is where the x location of shape 2's centroid is. Well, that's 1 foot to the left of the origin, or to the left of the y-axis, so -1 is going to be its x tilde. And shape number 3, this square, well, its centroid, at least in the x direction, is located at half of its width from its edges. So if its width is 1 foot, or its base is 1 foot, then half a foot away from this edge is where the centroid is located. However, we have to be aware that we are measuring from the origin. So to get from the origin to this location, we have to go 2 feet to get to the edge of this square, and then another ½ foot to get to where the centroid is located. So that's how we're getting negative 2.5 for shape number 3, because from the origin, we have to go to the left 2.5 feet to get to the x tilde location for shape 3. Now for the y tildes, for shape number 1, we're going to be measuring from this x-axis. So we go 1/3 of its height, and that's where the y tilde is going to be for shape number 1. So 1/3 of 3 feet is 1 foot in the positive y direction, so positive 1. For shape 2, it has a total height of 3 feet, so half of that will be 1.5 feet. So from the x-axis, we're going to have to go along the positive y direction 1.5, and that's where the positive 1.5 comes from. And for shape number 3, it has a total height of 1 foot, so it's going to be half of that from the bottom, so 0.5 feet. So as measured from the x-axis, we go positive 0.5 in the y direction, and we get 0.5. At this point, once the areas, the x tildes, y tildes are filled out, all of the hard part is done, and then we can kind of think of it as a spreadsheet, because we're going to next calculate the ax tilde. Most of the work is already done for this. We're going to take the value of a in this row times the value of x tilde in this row, and that's ax tilde. So 4.5 times 1, 4.5. A y tilde is the same idea. We are going to take the area times the y tilde for each shape. So again, 4.5 times 1 is 4.5. Go on and repeat that for the next rows. So for row 2 or shape 2, 6 times negative 1 gives us negative 6, and 6 times 1.5 gives us 9. Here we want to pay attention to the sign of our products. It is possible for our x tildes, y tildes to be positive or negative. So we see here our x tildes, because they are to the left of the origin, are negative. But it is also possible for our area to be positive or negative. Here they're all positive, they are all positive shapes. But when we cut out shapes, we can get a negative area. So notice when we multiply the a and the x tilde, or the a and the y tilde, that that could be a positive product or a negative product. It's possible that a and x tilde are negative, which would actually result in a positive ax tilde. So we just want to be careful on the signs here. So 6 times the negative 1 is the negative 6. 6 times the 1.5 is the positive 9. And finally for shape 3, 1 times the 0.5 gives us 0.5 for ay tilde. And the 1 times the negative 2.5 gives us the negative 2.5 for x tilde. So finally, when we've accounted for all the shapes, in this case the 3 partitioned shapes, we are going to sum down our columns. So down the area column, 4.5 plus 6 plus 1 is 11.5. We don't need to do it for the x tilde and the y tilde. That sum is not going to give us any information. Now down the ax tilde column, 4.5 minus 6 minus 2.5 is negative 4. And down the ay tilde, 4.5 plus 9 plus 0.5 is 14. So these ax tilde sums we're going to use to find x bar. X bar is going to be the total of our ax tilde divided by our total area. So negative 4 divided by 11.5. So to 3 decimals, that is negative 0.348 feet. And we can do the same thing to find y bar. We'll take the 14 divided by the 11.5, and we get a positive 1.22 feet. So again, this x bar, y bar is for this whole shape here, the location of its centroid. So roughly, if we go negative about 1/3 of a foot, negative 0.348, so to the left by 0.35 feet, and we go up by 1.22 feet, that is roughly here, not to scale, but roughly there is where the centroidal location of the total shape is going to be located.